Okay, perfect. All right, so we're gonna go ahead and get started. So this week, we're gonna cover a bit about what it means to be a universal approximator and why that's an important property, how neural networks are actually fulfilling that, and then we'll also get into in practice what that actually looks like. And then at the end, if we have time, I'll go over some code examples. So this is a bit of what I just said, just to introduce the idea. But generally speaking, I mean, approximation theory is a very old subject. And in this case, we're considering hypothesis classes is you can just think of that as function classes. In machine learning, they call it hypothesis classes because you don't actually know what the function is beforehand. You don't actually know what it is. You're trying to just use this architecture to sort of determine that. And actually, yeah, so Weierstrass has a lot of early results and sort of what kinds of functions you can use to approximate other kinds of functions, and also classes of functions that are, I guess, easier to approximate. In this case, we'll be looking at continuous functions. So if there's any questions about, like more like of the analysis details, I'm happy to answer that as well, but we don't need to get super far into it. So this is a pretty old result, 1865. So this is the Weierstrass's theorem. And so essentially this is about approximating functions with polynomials. And the key here is your polynomials have to be able to have sufficiently high degrees, so you can't have a fixed degree polynomial, right? Or else this doesn't work. And the way that he did this, the way that he proved this was by taking convolution and then applying Taylor's theorem. And so if you recall, I'll show on the next slide, but Taylor's series, that theorem involves actually having an infinitely differentiable function. Because if you remember the formula, you're taking like the, first derivative, second derivative, all the way down, and you're having these polynomial terms that you're like adding on at each point. But there is a more constructive proof than doing that. We're not going to go over that, but the point is the more constructive proof by Bernstein showed the idea of constructing sort of a class of functions that densely spans the space of continuous functions. And so that's really what the universal approximation theorem is getting at. It's basically trying to say, okay, we have a class of functions in which we can define by essentially multiplication by some matrix, adding some vector weight, and then some nonlinear activation function. And then, doing this, we can actually get sufficiently close to an arbitrary function, a continuous function. So, okay, so this is just really quick so you can see, but as you can see, you need the derivatives. You need to have as many derivatives to basically make this remainder term get smaller and smaller. And this was sort of like one of the early results in how to approximate functions. And again, like it's using polynomials, but like, you could do this, you could approximate, like sine, cosine. I'm sure you guys remember this is pretty much just 1b. Yeah, 1b, I'm pretty sure they go over this, but so this is what he used to prove it. And then, so now we can actually give the first definition. So again, soup norm is what we're looking at here. And so the definition is pretty straightforward. There's nothing too tricky. But the idea is universal approximator just means that we can get sufficiently close to this function. Now, that just tells you that we can. It doesn't tell you actually how to do that, and it doesn't tell you how fast this works. That's more of an algorithmic question. It turns out that for a lot of the methods, especially for like Taylor's theorem, like nobody actually uses that in practice to approximate things because it has slow convergence, and what we want is fast convergence. But the thing is, what we are originally interested in with sort of the foundation in terms of understanding neural networks is that we can actually approximate continuous functions up to arbitrary precision. So you can think of this sort of as a generalization of the Weierstrass theorem. Again, if you're familiar with real analysis, then this is nothing new to you, but this is stated in a bit of a different way. So this is stated in the language of using a universal approximator, but we have four properties that we need to consider. So we need continuity. This you can think of as identity. This is separation of points. And then this is closure under your operations. So if you can prove these four for your given class of functions, then that's really all you need to show that something's a universal approximator. And I'll give you guys just another second just to see. But okay, so again, just a quick refresh. We sort of went over this last week, so I'm not going to go too much in depth. But the neural network architecture that we're going to be focused on today is just it's called the multi-layer perceptron. This is a standard sort of feed forward network. When you see those pictures that look sort of like a neural network, that's what that is. There's more advanced versions of this, which we'll hopefully be able to cover later. But for today, I think it's probably for the best to just focus on this. And then here's the notation I'm gonna be using for this. So I'll keep consistent with this throughout the presentation. But again, this is pretty much, you can think of this as, this is just this is just a multiplication. We're adding a bias. We're applying a nonlinear activation function. And the choice of activation function, you can vary that depending on things like convergence, how fast you want it to converge. But in terms of finding universal approximators, we want to know sort of a general class of functions for which this will actually satisfy this theorem. So, okay, so putting in functional notation, just f of x. We can think of this as sending x to this. I just wrote as a dot product. Again, that's just our multiplication, the same sort of thing. And then we define this sort of span. This is our hypothesis class, as I mentioned before. This is the class of functions that are given by that. And this is this first simple result. So in practice, nobody uses cosine activation functions. But the reason that I'm putting this here is because this is going to be easy for us to sort of check the proof of that this works. So we can take that. So we'll use cosine as our first example.
Can you go back?
Yeah.
What was the why are we multiplying by C?
So C is so this is the thing. So sometimes in networks you can like adjust your output of your activation function by by just a coefficient, and then
Just to scale it.
yeah, just to scale it. Yeah. So like you can have C equal 1. It doesn't really, I think this is one of those things though where like I'm glossing over a few of the architectural details that actually can change how, the power you have to do this kind of thing. But for this, I think this is just a simple example just to sort of just understand this. Did this? Okay, so again, the original paper, so Hornick, Stinchcomb, White, they had one paper, Sabenko has one paper, Funahashi has another paper, all in 1989. So yeah, I guess they just sort of like looked at each other's and was like, I guess you could do this in another way. So the easiest way to do it was using the Stone-Weierstrass theorem. That's why I put that first, because that's what we're gonna look at. Sabenko and Funahashi, they use more advanced methods, which I'm not going to go over right now, but if you're interested, they use Hahnbach theorem, Rees representation theorem. So like if you're familiar with like functional analysis, Hilbert space theory, that's what they use to prove it. But you don't need to go that far to do this. So this is just a quick sort of just line by line of each of the properties we need to check. So continuity is more just, that's a pretty straightforward check. Again, so for identity, we have if we have this multiplication, we'll get cosine of 0 equals 1. And for separation, I mean, I can like go through and just say all of these, but the point is with cosine, you don't need to do too much work to sort of prove this, especially here for closure, right? Closure under addition is not that big of a deal, but under multiplication, because you have sort of the product to sum identity, you can sort of just expand this. So again, we didn't really have to use any really high powered math to sort of figure this out. But it's still a very powerful result because we know if we use cosine as an activation function in a neural network, then we could approximate any continuous function up to arbitrary precision. But we're not actually going to use cosine to do this. But
the only stipulation is that it's continuous. Like we don't think it to be like Like a norm space. I mean, like, is there anything else on it besides continuous?
No, it's just continuous. There are other versions of universal approximation theorem that you can have. There's some that are stated in terms of LP space. You like usually it's like L1 or L2, and then they have some even for Sobolev spaces. Like people just make results that are like, oh, here's some type of function, here's how I can approximate it, and then that's like a new paper. Do people actually use that? No, but you can do that as much as you want. Like you could just pull out everything you want. Yeah,
Like any
so
vector space?
yeah.
Okay.
And so this is the one that this is the result that I guess Stincombe and White's result was not they didn't actually like define what normed vector space that they were using for this. And then I can also like link those so we can like see that, but let me see. I guess yeah, there's a couple other things I want to say and then we could probably get back to that. But okay, yes. All right, awesome. So this is the more general version, which we're not going to go into all the details of how they actually did this, but the point is they define these sigmoidal activation functions, which they have this sort of limit property. So, and then you can vary this limit property. It doesn't always have to be this, right? There are different definitions you'll find out there depending on what you look at. So you kind of have to just sort of like standardize what you're talking about in the specific context you're talking about. But this sort of result covers all the activation functions that people generally do use in neural networks, which is like hyperbolic tangent, sigmoid, ReLU, leaky ReLU, like those kinds of things. And then, so the refinement of the theorem is now just replace cosine with any function that sort of has this like property. Again, this is just a more of a high level abstract view of how that works. And then here sort of you can see sort of like what these look like. This one usually ends up being the best, and there's a lot of research out there of why that's the best, which is more like that's more of an experimental thing. Like you actually have to like run tests and see. But the issue here is which we'll sort of get to when I discuss backpropagation, but these have derivatives, nice derivatives. This at zero doesn't. So usually people just define the derivative. They'll just say, oh, derivative at zero is something. And then they'll just put that into their like automatic differentiation function so that you can do backpropagation normal and not have to tweak too many things. But as far as being a universal approximator, that sort of implementation isn't really relevant. So let me see how much time I have. Okay, I want to go a little bit quicker. So this is this is the version you'll generally see of universal approximation theorem. If you look it up, see again, this is just that same that I had before. But here we actually have a bit more concrete definition of what spaces we're looking at. And sort of the like dimension of sort of these, but there are variations of this. So me telling you this isn't to say, oh, like this is the only thing that you'll see out there. Like this is just one that when people say universal approximation theorem, they're probably referring to this result. That's just sort of what the idea is. But again, the key here is this. The key is just we want to be able to get within epsilon of some arbitrary function. So, uh, so now we're moving on to how we actually do this in practice. And training neural networks is kind of like, I don't know. I mean, it's a lot easier now than it used to be because we have all of these like PyTorch and stuff. You don't really have to think about it that much, but in the past, it was definitely difficult. Backpropagation is based off of gradient descent. And this sort of idea this was like in the late 80s as well. Jeffrey Hinton came out with this. But the actual math for doing this has existed. I mean, the first occurrence of chain rule, I think was due to Leibniz, but it was like he had some mistake in it. It was like late 1600s. And then it was standardized by Lagrange in I believe maybe like 1790 something, and then like was very well known in textbooks. I think Koshi wrote a book that like had this in like and various forms of this, because there's like other ways you can, depending on, like with other certain types of functions, you might be able to simplify even further. But the point is, like, this has been around for a really long time. It just was, we're limited by compute capabilities to actually use this in an effective way. So only until maybe I'd say like the past like 15 years, 20 years has neural networks really been able to like take off because of like hardware acceleration capabilities. Um, so the backpropagation algorithm, again, I'm using the A and L notation that I had before. So it's in the slide. So if this looks confusing for a second, we can go back, but for time, I want to keep pushing on ahead. But what you're trying to do is you have a loss function L. And you can define this loss function depending on the type of problem you're trying to classify. A common one is cross entropy loss. This works for different types. It works for more than just binary classification. But you can envision with like, like a mean squared error or something like that, like those kinds of functions you can use as well. But really you're just differentiating with respect to your weights and your biases. And then it's called propagation because you're just adjusting. You start at the end of your network, you have like got some output, and then you're looking at sort of this, you're looking at this differential and then going to the initial layer of your network and saying, okay, we need to adjust the weights and bias by this much so that we can minimize this distance between our actual predicted output and then the true values. So this is a pretty straightforward algorithm in the sense that, yeah, I mean, it doesn't involve, you just, you have to actually like, again, you need differentiability. If you don't have that, then you have to like come up with some clever trick to make that work. But for a lot of the early work in this area, that wasn't really an issue. So yeah, and then gradient descent is what we sort of use this for. So this eta term is the learning rate. And then in the examples, you'll see what the learning rate actually does, but that sort of just is something that changes like how quickly it will adjust, how quickly it'll adjust sort of this change in the weights and the biases. And this is normal gradient descent. So the way this works is you have your entire data set, you put it into your neural network, and then you get some output. And then it sort of does this process on your entire data set. So the issue is you might fall, if you have like a really like complicated, like, let me just like, if you have like a function that's like this, and you're doing this sort of, you're like just picking some points and checking, you might like get stuck in this region and not actually check the other regions, but you have some like absolute minimum that you actually want to find. So then there's other versions of this, and this is where we get into sort of the optimizers. So one is stochastic gradient descent. So this is you, instead of doing it on your whole data set, you do it on a small batch. And so typically people do batch size of like 16, 32, 64. We can, the code example will make that more clear, but you want to do something small and then you sort of like smooth out over all of these as you're, as that sort of works. And then we have this. I don't want to spend too much time looking at this. I put this in the slides so that I send it to you so you can refer and look at this, but this is more useful for the code example. But this is another type of optimizer. This is sort of, I guess, yeah, this is sort of like physics inspired in a sense. Generally, when you see something like this row and then you have one minus, you should think about it's trying, like you should be thinking about like convexity. This is making something usually something that's a highly non-convex problematic optimization problem into smooth, a little bit smoother, easier to do. And this is a pretty solid optimizer, but it's not used as much as this. So Atom is probably the best one. Well, there's newer ones, but I mean, this came out in I think 2012. And so that's like pretty recent. I feel like, I don't know, like I like finished 8th grade in 2012. So like that was, I don't know. But this is one of those ones where, again, It's borrowing sort of the idea of stochastic gradient descent and sort of RMS prop, and then just adjusting the weights based off of this. So you have a bit of a smoother approach as well. Generally for Atom, you have your learning rate converges a bit better, a bit faster. Stochastic gradient descent, if you use small batches, sometimes you might get better results. So there's experimental trade-offs that you have to actually sort of work out and see. But again, so yeah, this is Atom. I know you said that you use this, but yeah, this is one of those, when we get to the coding example, we'll see you don't have to think about this at all. You don't even need to know what this is to do it. So let me go ahead and share.
Before we go to example.
Yeah, of course.
To the slide when we do backpropagation.
Yeah. Mhm.
Okay, so can you, and you mentioned something about you have different layers.
Yeah.
And what I'm thinking from the practical point of view, let's say I have like a lot of layers, a lot of weights, a lot of biases. I'm gonna multiply it by huge matrices. Yeah? How will, for example, basically large language models getting trained using backpropagation?
Oh, okay.
So basically, like,
Yeah.
so I don't understand like the process of backpropagation in terms of, like you said, like start from the end and go towards.
Yeah. So I guess there's probably a picture. The picture I have in my head, it'd take a bit to draw, but I think if is your question about how this happens in LLMs or just in general? Okay, because this is yeah. So the way this works is, let's say you have a neural network where you have one input layer, two hidden layers, and then an output layer. So nothing too complicated. You feed in your sorry. Okay, so you feed in your data set, and it's gonna do a bunch of those operations we talked about. It's gonna do the like matrix up, and then it's gonna do the activation functions, right? You get your output. And then what it's going to do is it will you have defined your loss function, right? And so what it's going to look at it's going to look at this loss between the actual values and then the values that you produce. And then what it's going to do with those is it's going to look at the difference, and then it will go back one layer. It will look at the sort of the output of the weights and biases in that layer.
So do you check with every single layer?
Yes, every single layer. So you go from so you have your
You can
output.
adjust every single layer one at a time.
Every single layer one at a time. So you first will adjust the I guess the second to the like last hidden
So you don't
layer.
adjust all the weights at the same time.
Wouldn't that be gradient descent, like true gradient descent would do just everything at the same time?
Yeah.
But like backpropagation is the idea of doing it layer by
Oh,
layer.
okay.
Yeah. Because gradient descent is like if you just, I guess in this sort of example, if you just had like, so if that's our arbitrary function we're trying to approximate, and I was using some neural net to do it, I could just, you can take the output of, so usually when you run a model, you will have an output of all of your weights and biases, and then you can just use that output and then try to just change those. Like you started off with some random inputs and then you can just try to change them all together. But backpropagation was shown to actually be much more effective for this. Again, this is in the paper, which I have not linked, but I can send all of the original papers for this stuff just to get sort of the idea of why people do that. But yeah, you do layer by layer. And the idea is by not doing everything all at once, that you it's supposed to solve a couple things, right? Because I think last time we talked a bit about overfitting, underfitting, and then like rate of convergence, those kinds of things. So the idea is you want to make sure that you're not just fitting random points to a curve, because if I were to, that's not generalizable. If I got new data, like say like in this example, this was like, I had some, like, say I was like doing, I don't know, like, say I had like healthcare data and like I had like a sample of like 1 million people, and this was what the like function I'm trying to like do looked like. And I got another sample of 1 million people, and then suddenly it's like just like flat. Like that would never happen, but like it actually was. This, if I just had like something that just was fitting this way too like accurately and just all the points like fall on here, then like it would just keep following this pattern and it would like miss something else, right? So we wanted to actually be able to account for this. So we want during the, I guess during the training process, when we update all the weights and biases, we want it to more smoothly sort of, I guess, do this, so it doesn't just like either one, like just, I guess, yeah, just like fit everything too close or get stuck in one of those sort of like, yeah, I guess the local minimum. But yeah, so you do it layer by layer, definitely layer by layer.
Yeah,
So yeah. So this is sorry. Yeah, go ahead.
Is that supposed to prevent you from getting stuck?
So it doesn't guarantee. It won't guarantee that you won't get stuck, but it's supposed to help you not get stuck because like, so like normal, like, okay, so let's say I have, I'm gonna do like just a 3-step backpropagation, right? So like, let's say here's my like, my first step is like, I could do something like, okay, like I jumped to here, I missed all of these, but that's fine because this isn't the absolute minimum. I'm searching for the absolute minimum, so that's okay. I jump to here, so then I jump to here. And then I might jump down here because I realize, oh, this is a little bit smaller. So this is step 1, step 2, step 3. This is where I found as the minimum, but this isn't the absolute minimum. So what Atom, RMS Prop, other optimizers might do is they might do something like, well, maybe here's your first step. And then your second step, it will do maybe a larger jump because it's a little bit smoother. And then it will do a larger one. And then here, say I stop the process here, right? Okay, like imagine that I drew this a little bit lower, then this would actually be better. But in practice, what happens is it really does depend on the data that you're working with. Because if you have, I mean, this function isn't that complicated. If it was very, very noisy, then you might have some cases where Atom doesn't do as well. And stochastic gradient descent does better if you just choose a really small batch size. So you kind of have to just like play around with it yourself in practice.
That really
Mhm.
slide where you, like, I think it was like the theorem about what is a universal approximator, like which classes. you use.
Yeah.
Like, forward.
Oh,
No,
this one?
No,
It's the first mention.
I think it was it was this.
like just before the 4 approximators, or before.
Oh, just before the like activation functions. The sigmoidal functions.
Yeah. Oh, okay, I think so this doesn't really cover leaky value.
No, this doesn't. That's a separate case. Yeah, they have to. Yeah, that's a separate one that they do with. Again, like these, there are results. There's like at least 30 universal approximation theorems, and there's probably more. There's probably twice that many because they have, like, oh, if you only use Toeplitz matrices, if you only use Hankel matrices, like you can start getting really crazy. So